Welcome back to Calculus. Today we're going to get ourselves started on the last section that we'll cover in Chapter 7. And it deals with fluid pressure and force. From science class, I hope you remember that pressure is equal to force divided by area, where force can be either measured in newtons, or in the US system, we could also measure in pounds. And then area is traditionally either measured in square meters or square feet. But we could also measure in square inches as well, or square centimeters, depending upon the application. All right, so some nice simple examples of pressure would be these two. What if we were to have a 200-pound person and the total area of their shoes, so they have two shoes on and the area is approximately 108 square inches, what would the pressure be? Well, it's going to be the force. So here the force would be represented by the weight of the person, 200 pounds, divided by the total area of their shoes. In this situation, 108 square inches. And if you were to do that calculation, then the pressure upon the floor would be 200 divided by 108, which is approximately 1.86 pounds per square inch. 1.86 pounds per square inch. Whereas if we have a 110-pound lady in high heels, and the lady in the high heels rocks back onto just her heels, so the total area of the shoes in contact with the floor would be half of a square inch. 1/2 of a square inch. Then the pressure is going to be the force, representing the weight of the lady, 110 pounds, divided by the area of her shoes, 1/2 square inches. And in this case, then the pressure on the floor becomes 220 pounds per square inch. All right, so just two examples of nice, simple, easy pressure problems. Okay, now we're not going to do too much with that because it's a little bit tough to integrate calculus into problems like that. What we're going to do instead is we're going to look at fluid force problems. Okay, and we're going to do that in two ways. We're going to do it where we look at the force upon a surface that is horizontal. Let me highlight that word. That is horizontal in a fluid. And then we're going to do it where we're going to be looking vertically at a surface in a fluid. Okay, so what's supposed to be represented by my picture here is that we have this huge tank that's 18 meters long, right? 18 meters long, 8 meters across, and 5 meters deep. It's filled with gasoline, which has a weight density of 6,602 newtons per cubic meter. All right, and then what we've done is we've laid a plate across the bottom of this tank. Okay, and you can see that the plate is meant to be a right triangle. Hopefully you can see the 90-degree angle I've tried to draw. And then the sides of the triangle are 1/2 meter by 1.2 meters by 1.3 meters. Okay, and so what we've done is we've laid this triangular plate across the bottom of the tank. In other words, we dropped it into the tank and it sunk down to the bottom of the tank. Now what I'm going to ask you to do is calculate the force acting upon the plate. Now this does not need any calculus, no calculus required, because the plate, think of it as a sheet of metal, think of it as a sheet of glass, think of it as whatever surface you want, but we've allowed this plate to settle on the bottom horizontally. It's not sitting up, it's laying down. So the force then is just simply going to be the weight density of the liquid multiplied by the depth of the plate multiplied by the area of the plate. And so without any calculus required, we just take the weight density of the liquid. So the weight density of gasoline is 6,602 newtons per cubic meter, multiplied by the depth, and if this tank was full of gasoline, the depth then would be 5 meters. And then the area of a right triangle is 1/2 times base times height. So in this case, the base is 0.5 and the height is 1.2. Okay. And then please notice before I punch out the math for everybody that the cubic meters that's in the denominator of the weight density would cancel with the meters and meters squared from the depth and the area. So the cubic meters in the weight density cancel with the meters and meters squared from the depth and area, and therefore our only label left is newtons. Okay, and then I'll just punch out the math for everybody. So 6,602 times 5 times 1/2 times 0.5 times 1.2. And if I've punched that out okay, what I've ended up with then, excuse me, is a force of 9,903 newtons. That's how much force would be pushing down upon that plate. But again, please notice, no calculus required, just simply multiplication of 3 factors. All right, let me just give you one more of those simple ones. All right, this time instead of it being a tank, I'm just going to assume that this is a lake. So this might be something like Burnside. And what we've done out on Burnside is we've dropped down a circular disc to the bottom of the lake. And we've dropped it to a place where the lake is 24 feet deep. So we've dropped this circular plate. We can think of it as a piece of metal, a piece of glass, even let's not use wood because someone might argue that it might float, but whatever the disc might happen to be, we've let it drop down to the bottom and lay on the bottom. So it's horizontal. The depth of the water in this location is 24 feet. My question to everybody is, what would the force on the plate be? Well, again, when it's horizontal, when the plate lays horizontal, it's just simply going to be the product of the weight density of the liquid multiplied by the depth of the plate multiplied by the area of the plate. And so in this case, the weight density is given to us in the problem, just like our dynamics problems. So this is going to be 62.4 pounds per cubic foot. The depth, as you can tell in the problem, is 24 feet. And the area of a circle is pi times the radius squared. And then the area would be measured in square feet. So again, just as we had on the previous problem, the cubic feet in the denominator of the weight density is going to cancel with the feet and feet squared from the depth and area. So all we'll be left with then is pounds of force. And when I do the multiplication for everybody, 62.4 times 24 times pi times 3 squared gives us 42,343.6 pounds of force. Okay? All right, so as an example, if you were to try to lift that plate off the bottom of the lake and keep it horizontal, you'd have to exert 42,343.6 pounds of force to try and pull that plate to the top of the lake. All right? You'd be lifting not only the plate, but you'd be trying to lift the entire column of water that's on top of the plate. You'd be trying to lift that whole column of water that would be laying on top. So that's how much force is being exerted directly down upon that plate. Okay? Now again, please notice no calculus is required there. No calc. All right? So what we want to get to then, finally, is problems that do require calculus. And this is going to be for problems that involve vertical surfaces. So we're still going to be considering a two-dimensional surface, some sort of plate, but this time it's going to be a vertical surface, so not horizontal but vertical. This one's going to require calculus, and the formula I'm going to ask you to use is this, that the force upon a vertical surface is going to be the definite integral from A to B of 3 factors. Now the factors you see are exactly the same as we've used in the previous 2 examples: weight density, depth, and area. Now the weight density again is going to be a given value. This is just going to be told to us in a problem. In any problem, we're just going to be told what the weight density of the liquid is. Then we have to consider the depth of the surface. And this is going to be the thing that now changes, because we're going to have a vertical surface. So when we have a vertical surface, either suspended in a lake, or whether it's the end of some sort of aquarium or gas tank or fuel oil tank, whatever it might happen to be, when we have a vertical surface, the forces vary. The force on the very top of the tank is not very much. Or let's say it like this, the force on the top, let's call it F1 for the first force, is a lot less than a force down at the bottom. Let's call it force 8 or something. Okay? The force at the top is a lot less than the force at the bottom. The reason being, because gravity is trying to pull this fluid down to the center of the earth, there's more, the deeper we go, the more liquid is pushing down, and therefore the force near the bottom is much greater than the force near the top. All right? And to accommodate these varying forces, that the force higher is less than the forces lower, what we're going to do is we're going to think about adding up all of the forces. We're going to add up the force at the top, then the next layer, next layer, next layer, next layer. We're going to add up all of the forces. And of course, that's where the integral comes into play. Whenever we add up a whole bunch of things in math, we integrate. Okay? All right, so one last thing before we get going with some examples. I just want to point out, let me do it in a different color here. The limits of integration, again, because of gravity, are going to be values off the y-axis. So the A value is going to be the bottom of the plate, the bottom of the surface, and the B value is going to be the top of the surface, the two-dimensional region that we're talking about. All right, and hopefully you'll see that in examples as we get ourselves started here. Okay, so make sure you get the formula down. Make sure you get the force integration formula down. All right, and now let's try some examples. Here's an example of one that might be a gigantic aquarium down at the Mall of America or somewhere. Okay, and what we're going to do is we're going to try to calculate the force on the end of the aquarium. Now I could actually pick any of the surfaces. I could pick the bottom, I could pick the front, the back, the left side, the right side, but I'm going to choose to find the force on this end of the aquarium. That's the surface I'm going to choose. Again, I could do the front being the side that's 12 meters by 6 meters, or the back or the left side, but I'm going to choose what I'm calling the front. And what I'd like you to help me do is calculate the force required. Now, because it's vertical, we're going to have to integrate, and the limits of integration are going to be the values that represent the bottom and the top of the surface. Now, to kind of work with that, what we need to do is we need to establish an XY coordinate system. And so what I'm going to do on this problem is I'm going to choose to put the x-axis right through the bottom of the tank, and I'm going to put the y-axis through the left-hand side. Again, just as in our previous section, you guys can choose to put the x and y-axis anywhere you want it. Anywhere you want it. But I'm going to choose to put it through there. So that my limits of integration then are going to be 0 to 6, because the way I've established the x-axis, the bottom of the tank is going to be located at y equals 0, and then our y values will go up, 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 1, 2, 3, 4, 5, up to the tippy top of the tank, where that top of the tank is going to be located at 6. And in fact, if you want me to just emphasize that, this value would be y equals 0. This value would be y equals 6, the way I've set that up. Okay? Then again, there's going to be three factors that we're going to integrate. And I'll abbreviate them above. Weight density of the liquid. Again, that's just going to be a given value. You can see it up to the right. Then, excuse me, the depth of any one of the layers. Remember, we're going to be integrating from 0 to 6, so whatever layer of liquid we're talking about, multiplied by the area of any one of those layers. Okay? So let's see if we can figure out these three factors. Weight density, again, given to us in the problem, so 9,810. The depth, all right, and I hope this sounds familiar, but the depth here is going to be 6 minus y. Right? Hopefully that looks familiar from our dynamics problems. We're essentially taking the top of the plate, the location of the top of the plate, and subtracting the value for y. So for any one of the layers, let's say we talk about the layer at y equals 4, just as an example, right? Let's take an example of y equals 4. So when y is equal to 4, right, that layer of liquid pressing on the front of the big aquarium, at y equals 4, what would the depth be? 6 minus 4 is 2. So we would make the depth of that layer 2. So I hope that makes sense to everybody. And then the area. So the next question is, depending on what layer you're talking about, let's talk about the layer very close to the bottom, or a layer in the middle somewhere, or one of these layers towards the top. Does the area change? Does the area change? Well, what kind of areas are we talking about, guys? Well, the areas we're going to be talking about are just little rectangles that are going to be infinitely skinny tall. Well, if they're infinitely skinny tall, if the height is infinitely skinny, that means we're going to have that be our differential dy. And then the width, so the width of every layer, whether it's this one or this one or this one or this one, do the widths change? From the tippy bottom to the tippy top, do the widths change? No, in this example, the widths are always the same. They're always 2. So if we think about the areas being the area of a rectangle, length times width, the lengths are always the same, 2. Actually, I did that backwards. Oh, shoot. I should have reversed that. Sorry, guys. I should have reversed that. The widths are always 2, and the lengths, I guess, are infinitely skinny this time. They're going to be our dy. Now, before we do any integration, please notice that just like our dynamics problems when we were pumping tanks dry, please notice that everything's in terms of y. The 0 and 6, we're off the y-axis. The depth is in terms of y, and the differential is in terms of y. Everything in our integral is in terms of y. Okay? Now let's go ahead and do the integration for everybody. We'll start by factoring out any factors. So I'm going to factor out the 9,810 and the 2. Please notice I can't factor out the 6 because there's subtraction going on. So I can factor out 9,810 and a 2, which allows me to pull out 19,620 on the outside of the integral. And the only thing I'll have left inside then is 6 minus y and dy. Of course, that's very easy for you guys to integrate. The integral of 6 is attached to the variable of integration, so 6y. And the integral of y is add 1, divide by the new. Vertical line to show us that we have to f-tick, and then we're going to be f-ticking from 6 down to 0. All right, so let me spread this out a little bit so everyone can see the math. All right, so everywhere we see a y, put in 6. So 6 times 6 is 36. 6 squared divided by 2 is 18. And then subtract, now everywhere we see a y, put in 0. So 6 times 0 minus 0 squared divided by 2. And I don't know what that was. There we go. And so what we end up with then is 36 minus 18, 0 minus 0. And so when I do that subtraction and multiplication, we end up with a total force of 353,160 newtons of force pressing on that front of the aquarium. Now I know this is a gigantic aquarium, but that's how much force would be pushing out on that front. When you add up all of the individual forces, that would be the total. So of course the aquarium engineers would have to understand what those forces would be and make sure they build an aquarium strong enough to withstand all of those forces. Okay? All right, so let's try another one. So here's a different type of a tank. It's a tank that's traditionally called a trough. It's got a triangular end where the triangle is an isosceles triangle. Excuse me. And then it's filled, in this case, with fuel oil. And the fuel oil has a weight density of 4,708 newtons per cubic meter. And what I'm going to ask you guys to help me with is calculate the total force on the end of the tank. Okay? And I'm just going to try to highlight that just lightly. So I'm just going to try and highlight that a little bit. This is the end of the tank that I'd like to calculate the force for. Again, could have picked the front, it could have picked this side, could also do that side, okay, or the other side or the end, but I'm just choosing this one. Okay, so I'm going to choose that end. So when we want to calculate that force, what we need to do is integrate. But to integrate, we need an XY coordinate system, so we need to put an X and a Y axis somewhere through that end of the tank. And I'm going to choose to do it this way. I'm going to choose to put the x-axis through the bottom, and I'm going to choose to put the y-axis right through the middle. Okay, so I'm going to establish my xy coordinate system like that. Again, there's multiple ways to do that. I'm choosing what I think is the easiest. All right. All right, now let's go ahead and set up our integral. First thing, limits of integration. Limits of integration are going to represent the bottom of that front of the tank all the way up, all the way up, all the way up, all the way up to the top of the tank. And from this value over to the left, you can see that that's going to be then integrating from 0 meters up to 8 meters. So it'll be integrating from 0 to 8. And then the three things that will be integrating are these factors: the weight density, the depth, and the area of every one of the layers. Now remember, the layers are just simply going to be rectangles, so we're going to be multiplying lengths times widths. Now the weight density, again, is always just going to be a given value. So for us in this case, the weight density is 4,708, and the depth is just the top of the tank minus whatever y value layer we're talking about, whether we're talking about a layer at the top, somewhere in the middle, or way down at the bottom. The depth is just going to be the top of the tank, the top of the surface minus whatever y value we're on, anywhere from 0 up through 8. Okay? And now finally, the toughest one is the area. All right, so we have to actually think about what some of these would look like. So here's a layer of water, or here's a layer of water, or here is a layer of water. Now again, all of these layers are going to be infinitely skinny up and down because of gravity. So therefore, one of the dimensions for our areas is going to be infinitely small, so that becomes our differential dy. All right? Then the other one is going to be the horizontal measure, right? The horizontal measure. Okay? And of course, you can see that that varies. At the tippy top, we know that the topmost layer is 6 meters long, but towards the bottom, they get smaller and smaller and smaller. So how can we accommodate for that different value, for that value that changes from the top down to the bottom. Okay? And the idea is we need to figure out what the equation for this line is. Let me highlight it for everybody. In fact, let me highlight it in blue. And if I draw it a little bigger so everybody's eye catches it. So what I'm going to need is the equation of that line. Okay? Just help me out. Let's get this equation. Only takes a little bit because equations of straight lines are real easy. What would the equation of that really dark, heavy blue line be? Well, what we need, of course, is two values. We need the value for the slope and we need the value for the intercept. Now, because of the way I've drawn my XY coordinate system, where would that line cross the y-axis? Well, it would cross at 0 because I put the XY axis right at the bottom of the tank. And so the other value we would then need is the slope. All right, and the slope is going to be rise over run, and the rise and the run are going to be represented by the height of the tank, 8, and the run of the tank. Now, because the tank was in the shape of an isosceles triangle, when we draw this line in, that cuts the bottom into two equal chunks of 3. Therefore, the slope of that line would be 8/3. Okay? Now, we don't want to leave it in terms of y equals 8/3 x plus 0, because if we go back to our definite integral, the 0 and the 8 were values off the y-axis. The depth is in terms of y. The differential is in terms of y. So we need to make sure this varying length is also in terms of y. So what we're going to need to do is solve this equation for x. So if we solve this for x, we'd have to multiply both sides by 3/8. And so x is going to be equal to 3/8 y. But there's just one little hiccup with that. I know everybody's tempted to just now put in 3/8 y for the lengths of all of those layers of water. But unfortunately, it's really tricky. That only gets me the distance, guys, from the y-axis to that line. That only gets me the distance from the y-axis. Please notice where I'm drawing arrows here back up on the picture. That only gets me the distance from the y-axis to that line. Y-axis to that line. Y-axis to that line. All right? We need the distance all the way across. But because it's an isosceles triangle, the triangle on this side is going to look the same as the triangle on this side. And so that means we have symmetry going on. And therefore, the actual length is going to be 2 of those. 2 of those. Okay? That's probably the hardest part of this entire problem. Feel free to shoot me an email or give me a call if you want to talk that through a little bit more. Okay? That would be the complete setup. And now I'll work through the integration for everybody. Again, taking out any factors that I can right off the bat. So what I'm going to do is start by factoring out the 4,708, the 2, and the 3/8. And what I'm able to factor out then is 3,531. Let me double check that. Yep. And what I'm left with then is an 8 minus y, a y, and a dy. Now to integrate that, of course, I need to use the distributive property because we don't have a product rule. So I'd need to distribute y times 8 and y times negative y. And now I'm all set to integrate by adding 1 and dividing by the new, adding 1, dividing by the new. And then we'll be f-ticking from 8 down to 0. So let me spread out a little. Everywhere I see a y, put in 8. So 8 times 8 squared divided by 2. I think I punched that out okay. I got 256. And then 8 to the third divided by 3 would be 512 thirds. And now subtract and put in 0. So 8 times 0 squared divided by 2, and 0 to the third divided by 3. Both of those fellas would be zeros. So when I subtract 256 minus 512 thirds, I get 256 thirds. Oh yeah, that makes sense. And then when I multiply by 3,531, we get 301,312 newtons of force on the end of this tank. Let me shrink this up so you guys can see the whole thing in one shot. There you go. That's the whole works. Okay? Now this video has gotten pretty long, so I'm going to stop this one. I'm going to have 2 more example problems that I need you guys to look through so that you know what you're doing in the assignment. So take a break, have a little diet dew, and then come back and watch the next video. It should be much shorter. We're just going to talk through 2 more examples. All right? See you soon.